Hi, I'm Theo. In this video, I will present our paper, When is Deep Learning the Best Approach to Knowledge Tracing? That will appear in the 2020 edition of the Journal of Educational Data Mining. This is joint work with Ken Codinger and my advisors Jeff Schneider and Tom Mitchell at CMU. As the name of the paper suggests, I will discuss the conditions in which deep learning is the best approach to knowledge tracing, and more broadly, the circumstances in which a knowledge tracing algorithm outperforms others. I will first present the context for this work, what are intelligent tutoring systems, and what is knowledge tracing. Then I will quickly introduce the three most common families of knowledge tracing models in use today: classical logistic regression and Markov process models, and modern deep learning methods. I will then motivate the problem we address, present our approach, followed by results, and conclude with takeaway messages for both industry practitioners and researchers. So, what are intelligent tutoring systems? An intelligent tutoring system is a computer system that aims to provide customized instruction or feedback to learners, usually without the intervention of a human teacher. So, how do intelligent tutoring systems enable customized instruction? First, they estimate the current state of a student's knowledge. Then, they provide teaching materials, like lectures and exercises, adapted to the state of knowledge. But what does it even mean to estimate the current state of a student's knowledge? In other words, how do we formalize knowledge? This is where knowledge tracing comes into the picture. We cannot directly measure knowledge, so we settle for what we can actually measure: the student's performance on exercises solved. What the student knows is then synonymous with what the student can do. Given a student's history of exercises solved, we predict future performance on unseen exercises. With this estimate in hand, there are many ways to customize instruction. A commonly used one is to recommend exercises that are estimated to be at an optimal level of difficulty, not too hard nor too easy. More formally, at step T, the student solves question QT, and AT denotes the correctness of her answer. 1 if the answer is correct, 0 otherwise. The tuple xt summarizes the Tth interaction of the student with the system, and x 1 through T denotes the history of all previous interactions. We want to estimate P of AT plus 1 equals 1, given QT plus 1 and x1 through T, the predicted probability of success on the next question, given the history of previous interactions. In this paper, we compare three families of knowledge tracing models. The first family, logistic regression, is a logout linear model with a long history in the educational data mining community. Different feature sets yield various models in the literature. In our experiments, we considered item response theory, IRT, performance factors analysis, PFA, and DA83H, the best paper at JEDM 2019. Details of the features of these algorithms are not important for the rest of the talk. The second family, Markov processes, also has a long history in the community and includes the original and still most widespread knowledge tracing model, Bayesian knowledge tracing, or BKT. In our experiments, we consider its best performing improvement to date, which relaxes some assumptions, and is termed BKT+. The third and final family, deep learning models, made its apparition in the EDM community more recently with deep knowledge tracing, TKT, a recurrent neural network applied to the knowledge tracing problem. In our experiments, we also include self-attentive knowledge tracing, SAKT. In the subsequent slides, I will highlight algorithms by their family scholars. Now that we've covered a little bit of background on knowledge tracing, I will motivate the problem we address. So, which knowledge tracing model should we use? Or in other words, what knowledge tracing algorithm makes the most accurate predictions in what conditions? The original deep knowledge tracing, DKT, paper claimed that DKT outperforms Bayesian knowledge tracing, BKT, by a large margin of 25% AUC, a measure of prediction accuracy. But one subsequent paper showed that DKT does not outperform classical algorithms, BKT and PFA, by as large a margin as initially reported. Kaja and al. Go one step further and even show that BKT with relaxed assumptions, a method they term BKT+, can outperform DKT. Similarly, Wilson and al. Show that Bayesian extension of item response theory, arguably the simplest knowledge tracing model, can also outperform DKT. But these comparisons are not entirely satisfactory. First, there is almost no overlap between the datasets used in different papers, leaving us in the dark as to what algorithm performs best overall. And most importantly, none of these works investigates in what conditions an algorithm outperforms others. Now that I motivated the problem we address, I will cover our approach. We systematically evaluate 3 families of knowledge tracing models to determine what characteristics of a dataset lead to a method outperforming others, and what components of an algorithm explain its performance. We evaluate knowledge tracing models on 9 real-world datasets exhibiting a broad range of properties. 4 datasets from the Assessment Intelligent Tutoring Systems, 2 datasets from the KDT CUP 2010 Educational Data Mining Challenge, 1 dataset from middle school students practicing Spanish exercises, 1 dataset from a college engineering statistics course, and a dataset from the Squirrel AI Intelligent Tutoring System, a popular intelligent tutoring system in China. This dataset is not yet published. The 9 datasets vary by size, as measured by the number of learners, the number of different questions, which we also refer to as items in subsequent slides, the number of different knowledge components, which you can think of as higher level skills associated with each question, and the number of questions solved, which we refer to as student interactions with the system in subsequent slides, and the number of interactions per student, which we will cover in more detail. This table describes our dataset statistics, with features on the left and dataset names on the top. Don't worry about interpreting the table yet, I will guide you through the relevant numbers in the next few slides. The first 4 features, total number of interactions, number of learners, number of items or questions, and number of knowledge components, represent the dataset size. We found the size of the dataset most directly influences the relative performance of knowledge tracing models. This is because each model needs a different amount of data to generalize well. When considering the statistical generalization of knowledge tracing models, the dataset is small if it contains few learners that attempt each question. For example, the Assessment's 2009 dataset, ASSIS09 in the table, is small as it contains relatively few total interactions and learners, but covers a considerable amount of items and knowledge components. In comparison, the Squirrel AI dataset is large, as it contains many more total interactions and learners, for about the same amount of material covered. The second characteristic of a dataset with a significant impact on performance is the number of interactions per learner. You can think of this as the length of a sequence of questions that each learner solves. The Assessment's 2009 dataset contains short sequences. Each student solves an average of only 32 questions. In comparison, the Spanish dataset contains long sequences. Each student solves an average of about 3,000 questions. In terms of evaluation methodology, we used 5-fold cross-validation at the student level. This means we split the student population into 5 decision groups and perform cross-validation on this basis. We report metrics across the entire dataset when each data point was in the test set once, and standard deviation across folds. We compare all approaches in terms of AUC, a measure of prediction accuracy, and root mean squared error. Our code and links to public datasets we use are available on GitHub. Next, I will present our results. I will first present an overall comparison of the 3 families of knowledge tracing models on the 9 datasets we consider. Then I will dive into the effect of dataset characteristics. And finally, I will give you a taste of the experiments we ran to investigate the impact of algorithmic choices. The logistic regression model with the best set of features, which we will refer to as best LR in the subsequent slides, leads on 4 datasets out of 9. Deep knowledge tracing, or DKT, leads on the remaining 5 datasets. Bayesian knowledge tracing, or BKT, lags behind these other approaches, and BKT Plus, its best performing improvement to date, is competitive but too slow in large datasets. Next, we will investigate the relative performance of the leading models, best LR and DKT, as a function of dataset characteristics. We observed 3 phenomena. First, DKT overfits small datasets, and logistic regression underfits large datasets. Second, DKT fails to retain long-term information. And third, DKT better exploits temporal information. We will cover the evidence supporting the first 2 hypotheses in more detail in the following slides, but in the interest of time, we refer you to the paper for evidence supporting the third phenomenon. Our first observation is that deep knowledge tracing overfits small datasets, and conversely, logistic regression underfits large datasets. For example, this table shows algorithms on the Assessment 2009 dataset sorted by their AUC. Higher is better. As you can see, logistic regression dominates on this dataset. This is because DKT overfits. Conversely, on the Squirrel AI dataset, which is large, the trend is reversed. DKT takes the lead. To confirm this hypothesis, we ran an additional experiment varying the amount of training data on the Squirrel AI dataset. On this graph, the x-axis is the size of a subsample training set, and the y-axis is the AUC. Higher is better. We can see that logistic regression dominates in the low data regime, while DKT takes over in the high data regime. Our second observation is that DKT fails to retain long-term information. This plot shows the distribution of the number of interactions per learner. Most datasets exhibit a power law distribution with up to a few hundred questions answered for the typical learner, like the Squirrel AI dataset on top. But some datasets, like Spanish, are outliers. They do not exhibit a power law distribution and contains thousands of interactions per learner. As you can see in this table, DKT underperforms on search datasets. We hypothesized that this is because DKT cannot keep track of long-term information. This is a well-documented problem of recurrent neural networks. This figure shows the performance of DKT and logistic regression as a function of the amount of training data available per student on the Spanish dataset. DKT plateaus when the history contains more than 1,000 questions answered, whereas logistic regression keeps improving with more data. This confirms our hypothesis that DKT cannot keep track of long-term information. In contrast, approaches operating on a feature vector of historical counts, like logistic regression, sidestep this issue. Now that we have covered the effect of dataset characteristics, I will give you a taste of the experiments we ran to investigate the impact of algorithmic choices. We ran 2 ablation studies to investigate what components of leading algorithms explain their performance. Our first ablation study compares different feature sets for logistic regression models and a feed-forward neural network with the same features. The second study compares different combinations of inputs and outputs for deep knowledge tracing. In the interest of time, I will only present results for the second study. Deep knowledge tracing can process as inputs either item embeddings or embeddings of the knowledge components associated with items. This reduces the amount of information available, but helps generalization because datasets contain many more learners per KC than per item. Similarly, DKT can output either an individual probability of success per item or a common probability of success for all items in a KC. This reduces the granularity of predictions, but also favors generalization. Prior works often use KC inputs and KC outputs, without explicitly discussing the effect of this modeling choice. This table shows the AUC for different combinations of inputs and outputs. Higher is better. We can see that the choice of inputs and outputs considerably impacts performance, that the best option is often KC inputs, but item outputs. This goes against established practices. To conclude, I would advise practitioners to avoid microprocess models, to use DKT on large datasets and try both questions and cases as inputs and outputs, and to use logistic regression on small datasets, and try all combinations of features, referring to the ablation study in the paper for guidance. In terms of research, the main takeaways from the material we've covered in this talk are that there is value in evaluating new algorithms on a broad range of datasets. With modern datasets increasing in size, deep learning is here to stay, and we need deep learning models that better retain long-term information. There is also much more in the paper that I did not have time to cover in this 15-minute talk. Thank you! We hope our open source Python implementations can be useful to the community as baselines for future research, and we wish you a great online conference experience.